Okay. All right. So today we're going to cover something called the limit laws, and we're going to kind of slowly develop those, and then I'll show you what it means when they ask you to justify the limit in your solutions as you go through, and then show you how we typically go through and do these. So on this starter question, it says use a chart or a graph to evaluate the following limits. So we've got the limit as x approaches 2 of x plus 4. I mean, we probably have a darn good guess as to what the answer is on that. But if we were to look at that line, cross is a 4, slope is 1. Okay, the point of interest is 2. The graph would get really close to this point from either side. There's nothing weird that happens on that. So what's the limit here? Limit would be 6. Okay. This one's a little bit more complicated. If we were to think of what the graph of this looks like, and I'm hoping that based on what you learned in pre-calculus and what we reviewed last week, you can kind of come up with roughly what this would look like. We know this has a domain problem at -2. It doesn't cancel, so you know you've got a vertical asymptote at -2. The leading coefficient here is 1, the leading coefficient there is 1. It's degree 1 on the top and degree 1 on the bottom, so this would have a horizontal asymptote of y equals 1. And it has, let's see, if you plug in a 0, you end up with 1/2. And if you plug in, let's see, if you set that equal to 0, what would be the x-intercept for this graph? Yeah, it'd be -1, okay? And I'm going to do this in red, okay? So it's got a point there and a point there. And based on what you know about rational functions, hopefully you know it's got to have a branch that looks like this. And then if there are no x-intercepts over here, the other branch has got to look like that, okay? Now, we could pick numbers that are really close to +1 on either side. So we're interested in what the function value is approaching as x approaches 1 from either side. But it approaches from here and here. Again, nothing weird happens. We don't need to be too terribly careful. So we could probably get the answer by just plugging in 1. So we'd get a 2 on the top and a 3 on the bottom, and that would be 2/3. And does that look about right based on what the graph is? Okay. And we could also throw that in a calculator, have it compute a bunch of values, and we'd get really close to 0.6 repeated from each side. So these types of functions right here, even with this asymptote, they're not too bad for finding the limit, because we weren't finding the limit at any point where we have a domain issue or something weird happening on the graph. Holes or jumps or vertical asymptotes or different things like that. All right? But a lot of times you're not going to be able to have a graph or a calculator handy, and you're going to need to be using analytic techniques. So you're going to need to use paper and pencil techniques and use the calculus tools that we're going to talk about in order to compute limits. Okay, and a lot of that involves some algebra, but we're going to start off pretty simply. Actually, it's pretty easy to figure out. So on the examples that we had up above, if you looked at the graph, this limit was exactly the same as the function value there. So that 0.26 is on the graph. That 6 was our answer. Okay, and this point right here, if you plug it in, you get 1, 2/3. So the limit was the exact same as the function value at the point of interest. And we're going to kind of develop a technique, and this technique is called the direct substitution technique. Because really, I mean, what did we do up above here? I mean, we basically just plugged it in, right? So let's talk about why we can do that. And we're going to build these rules, these limit laws that we're going to be able to use, starting with the most basic one. So if I were finding the limit as x approaches -4 of the function 2. Now we kind of broached this yesterday where we were talking about, well, the variable in the limit, the only thing that changes is x. Is there an x in this function? There's not. And we could also look at this function. This function is the line y equals 2. So no matter what the point of interest is, what's our limit going to be? Our limit's going to be 2. So the limit as x approaches 0 of -3, that's going to be -3. So if we were to state a rule, if you're dealing with just a plain old constant, The limit as x approaches a of the constant is just the constant. So the limit of a constant function is the constant. If it's 2, the limit's 2. If it's -3, the limit's -3. Okay? So that's about as easy it gets as far as a function value, okay? A constant function. Okay, now let's talk about what we get when we have an identity function, okay? About the next easiest. So what we're talking about here is we're dealing with the identity function y equals x. Well, think about what that looks like. Nothing weird happens on that. If I were finding the limit as x approaches 2 on the identity function, so the limit as x approaches 2 of x, we're talking about that point right there. What is it? It's just 2. Okay? The limit as x approaches 0. As we approach 0 from either side, the function values get closer and closer to 0. I mean, it's called the identity function because whatever you plug into it, it doesn't change it at all. It maintains its identity, so to speak. Okay? So if we're interested in the limit as x approaches 2, you get 2. If you're interested in the limit as x approaches 0, you get 0. So the limit as x approaches a of the function x is just a. Or if we said this in words, the limit of the identity function has the same value as the point of interest. So wherever we're trying to find the limit, that is in fact going to be the answer. Okay. All right. So since the limits of these two types of functions, since they exist, since we get a nice real number for those, okay, since that limit exists, okay, we can do a bunch of arithmetic on it. We can add them, we could subtract them, we can multiply them, and we can divide them. Okay, you have to be a little bit careful with dividing because you'll remember last week we said if you have division in a problem, you've introduced a domain issue. You've got to be careful that the denominator is not 0, okay? So we're going to say as long as there are no domain issues. There's not going to be any problem with adding, subtracting, or multiplying. It's when we divide that we've got to be a little bit careful. And what we're going to do is we're going to use these two ideas right here in order to produce some other rules. So these limit laws or these limit rules are down at the bottom. It says suppose c is a constant and these limits, limit as x approaches a of f of x and the limit as x approaches a of g of x exist. In other words, when we say they exist, they're a number, okay, a real number, not infinity or negative infinity or does not exist, okay, it's a number, okay? Then this is true. The limit as x approaches a of f of x plus g of x is the limit as x approaches a of f of x plus the limit as x approaches a of g of x. In other words, you can find the limit of the two separate terms, those two separate pieces, and then add them together and get the same result. So let's take a look. The limit as x approaches 1 of x plus 6. Now, technically, this is how you'd apply this. This is how you would justify using that. We're going to break this into the limit as x approaches 1 of x plus the limit as x approaches 1 of 6. What we've done is we've taken a new problem and we're going to use those two results that we found previously. This is the limit of a constant. Does it change at all? Nope. So that part's a 6. This is the limit of the identity function as x approaches 1. What's that?
1.
That's going to be a 1. So we add those together, we get a 7. Now, in practice, what we typically do, if you had to justify and show work, this is the work you'd show. But in practice, we're going to do this. We're going to look at this and say, okay, we're finding the limit as x approaches 1 of x plus 6. Well, that doesn't change at all. That stays a 6. What does that approach? That approaches a 1. We're going to add them together and we're going to get the same answer there. It works for subtraction also. So does everybody understand the difference between what we're doing for the work as a shortcut and what we're thinking through and how you'd actually go through and justify using the limit laws? Okay? I'll do this on the next page, but for right now, x is changing. That doesn't change the 7. X approaches a 2, and it works with subtraction also, so the answer on this one is 5. Tell me if I make a silly mistake here, okay? Here's the next limit law. This is called the constant multiple rule. This is kind of cool. The limit as x approaches a of a constant times a function is the constant times the limit of the function. Okay? So you can find the limit of the function separately and then multiply it by the constant after the fact. So it's kind of like sliding that c out in front and then multiplying by it after. And again, if we used the justification for this, here's what we'd do. We'd have a -8 out front, and then the limit as x approaches 3 of x, again, using that idea that we found previously, -8. The limit here is going to be 3, so my answer is -24. Again, in practice, that's a -8. That approaches a 3. Multiply them together, you get -24. Any questions there?
So for homework-wise, you want us to show all the steps?
It depends on what it says. If it says find the limit, just find the limit. If it says justify your answer, you'd want to probably put some justification. But if there are 5 problems like that, I'd probably do 3 of them with justification and the other ones I'd just do quickly. Okay? Good there? Okay. This one says if we know those 2 limits, you can find the limit of each piece separately and then multiply them after the fact. So if you found the limit of this piece, it would be 4. If you found the limit of this piece, it would be 4. So the answer is 16. Good? Okay. And this last one says you can find the limit of the top and the bottom separately and then just divide the 2 as long as the limit for g is not 0. Okay? So on this problem right here, the top approaches a 0, the bottom is a constant, so it stays 9, so the end answer is 0 on this one. Any questions there? Make sense? Pretty easy? Okay. All right. So there are a couple of other theorems that would help us find limits of more complicated functions. And it turns out, I've got a couple of them listed here. It turns out you can take a limit and raise it to a power. And you can take the root of those functions that you're finding limits of, okay? And you can find the limit of that, a more complicated function just as easy as long as when we raise it to a power or we take the root, we're not introducing any domain issues, okay? And when we deal with more complicated ones, remember domain issues would be like dividing by 0 or taking an even root of a negative. So we've got to make sure that we're not introducing any of those. So this one says, if I'm trying to find the limit of a function raised to a power, I can do this. I can change the order. I can find the limit and then raise that limit to a power. Okay? And it says you can do that for any positive integer. Any positive integer. So if you can do it if the power is 1 or 2 or 3 or 4 or so forth. And we actually saw kind of an example of this. What would be another way to write this one right here? X squared. So you could find the limit as x approaches 4 of x, which would be 4, and then square it, you get 16. Okay? Cool. And it works with roots also. So if you're finding the limit of a function where you took the nth root of that function, you could find the limit of the function and then take the nth root of that limit and you'll get the same answer. Okay? Again, you've got to have a positive root right here, so it's got to be the second root, third root, fourth root, and so forth. And then we make this assumption, if n is even, and this takes care of that domain function right here, we're assuming that that limit is non-negative. Okay? Everybody good there? All right. And let's see. I'm not sure why they said it needed to be positive here. Even if it was 0, wouldn't that be okay? Yeah. Yeah. That would be fine because the nth root of 0 is 0. So that would be fine there. Okay, so what we're going to do here is we're going to use some fairly simple limits and one that we already know. You may not know what these functions are, but I'm telling you the limit as x approaches 0 of f of x is 2. So the limit exists. It's the real number, positive 2. The limit as x approaches 0 of g of x is the real number, -8. So it exists. The limit is -8. And then this one right here that I said you're going to want to keep track of this one, kind of put that in your tool bag. The limit as x approaches 0 of sine of x over x is 1. Okay? Now, what you do need to notice is that on every single one of these, the point of interest is the same. Okay? And that's important. Okay? You'll notice that in every one of these, limit as x approaches a, limit as x approaches a, they're all at the same point of interest, which is what we've got right here, okay? So let's do this as easily as we can. We could go through the justification for this and actually break it up, but what is the limit for this piece? That one's 2. What's the limit for this piece? -8. Okay, technically we'd write it like that. We're going to end up with -6. Okay? I'll do this one by justification. I'm going to use the constant multiplication property here. So I'm going to do 5, limit as x approaches 0 of f of x. Then I'm going to do -4. Again, slide that out there. And then this is the limit as x approaches 0 of g of x. So this is 5 times. That limit is a 2. This is -4. And that limit is -8. So I've got, let's see, 32 plus 10. So the limit here is going to be 42. Any questions? Okay, so I use the constant multiple law, and I also use the subtraction property there. Okay? All right. Let's take a look at this one. Again, let's do this the easy way. What is this limit? What's the limit as x approaches 0 of f of x? That one's 2. So that piece, the limit of that piece, the limit of that factor is 2. What about this one here? That one's 1. So our answer is just 2. That's simple. Top approaches 2, bottom approaches -8. Oops, -1/4, right? How about this one? Okay, that approaches -8, and then we're going to square that. So we find the limit of the function, then we apply the exponent. So we're going to end up with 64 right there. And how about this one right here? Raised to the 1/3. Now, we didn't have a rule that said you could have, well, wait a minute. This said positive integer. We've raised it to a power, but what does that represent? Represents the cube root here, okay? So I can find the cube root of the limit as x approaches 0 of g of x. That's the same as the cube root of -8. So my answer is -2 is the answer on that one. What if that exponent right here had been a 1/2? Couldn't have done it because we'd have an even root of a negative, and we said that didn't work. Okay? Any questions there? Okay. So this just said find the limit, and we did most of them kind of the short way. This one says evaluate and justify each step. So technically, again, here's what you'd do. You'd do the limit as x approaches 2 of x. We'd square that. Again, notice how we've changed this into the problem that we started out the class with. Just finding the limit of the identity function. Then the limit as x approaches 2 of x. And then minus the limit as x approaches 2 of 7. A lot of writing just to get an answer that you could just plug the 2 in and get. Because when you plug in a 2, you get 2 here squared, so we get 4. Limit of the identity function again, 2 times it by 3, we get 6. Constant function, same as the constant, so minus 7. So the answer on this one is 3. Okay, so again, I'd choose wisely. If it says justify on 14 different problems, once you get the idea and how to write it, I'm not interested in you knocking yourself out, spending 5 lines doing one simple problem, because this is pretty easy to find the limit. What does the top approach? 7, and the bottom? Yeah, this would be a 0, so that's going to be the square root of 16 plus 4, so that's going to be an 8. There's the answer. If you were to go through and justify, again, technically you'd have to write this. 5 limit as h approaches 0, h squared plus limit as x approaches 0, 7, and do all of that sort of stuff. And you'd have to take the square root of the limit of that function and a bunch of different pieces and stuff like that. Okay? So, do I need to write all this? Maybe on a couple problems, okay? But just realize when they say justify, that's what they mean. They mean show every single step in how you're applying the limit laws from this section, okay? All right, let's just talk about this next one. It's got an even root, so should we be careful? We should be a little bit careful. You can't just plug in anything you want. We want to make sure that we don't have an even root of a negative. If I plug in a -4, this is going to be 25 minus 16. That's going to have me finding the square root of 9. And are we okay with that?
Yes.
We are. So the limit there would be 3. What if that were a -10? So the limit as x approaches -10. Wouldn't be okay because we'd have 25 minus 100, finding the square root of -75, not a real number. We're interested in real number answers here. Okay, are there any questions there?
Would that just be undefined?
Yeah, we'd say undefined or does not exist. How would you justify what? This one right here? If we were to go through and justify, we'd do a big square root, and then we'd do the limit as x approaches -4 of 25 minus the limit as x approaches 4 of x quantity squared. Does that make sense? Sure? Okay. All right. So, I mean, if you look at this on all the problems that we've done so far, as long as you're using your head and you're not coming up with any domain issues like even roots of negatives or dividing by 0, you can do substitution. I mean, it's a good idea, in my opinion, to think, okay, as x approaches 2, this is going to approach 2 squared, which is 4, okay? If you want to just plug it in and get 4, that's totally fine, but you ought to at least think, we're getting close to 2, so this is going to get close to 2 squared, and that sort of thinking. But really, you can use substitution for a lot of them, unless they get more difficult, which is what we're going to show right now, ones that can't be done using substitution. Yeah.
On the previous one, we wouldn't write that as plus or minus 3, would we?
No, because remember, whenever a radical is in a problem, we're talking about the principal root, and the principal root has the same sign as whatever's underneath. Since it was a +9, the answer is going to be positive. If we put a square root in a problem, then you have to worry about the plus or minus. If it's there to begin with, then it's just the positive one. Good question, though. Anything else? Okay. So when you're going through and doing these homework problems, you want to go, okay, can I use the addition property? Can I use the subtraction property? Can I use this constant multiple property? Okay? But sometimes you'll run into things where you can't do them by substitution. For example, this one right here, you can't plug in the -1. And I actually showed you the other day how we'd approach a problem like this. So if it's not one of those laws there and you can't do it by substitution, we need to manipulate it using some algebra so that we can do it by substitution. And here's how that would work. So what we're going to do is we're going to factor and or we'll simplify. So is it possible to factor it and simplify it so you can do it by substitution? Our goal is to get it to a point where through algebra we can do it by substitution and we can know for a fact what it is. We might rationalize the numerator. In algebra and college algebra and pre-calculus and stuff like that, we spend tons of time rationalizing the denominator. There's a good reason for that, okay? It's hard enough to work with fractions, let alone fractions that have ugly numbers like radical 13 in the denominator. So we spend a lot of time learning how to rationalize denominators. Turns out in calculus, sometimes it's useful to have the top be a nice number, a nice rational number on the top, and some old ugly number on the bottom, okay? And you'll see that in just a second. Okay, use a familiar limit. Use some of those that we're already aware of, some of those that I mentioned that you ought to keep track of, like this one right here. Limit as x approaches 0, sine x over x equals 1. Okay, and consider one-sided limits. If you can't figure out what the two-sided limit is, maybe figure it out what it is from one side and from the other side. So figure them out separately. And if it's going to have a limit, the two of those have to agree, okay? So figure out one side, then figure out the other side and see if they agree. And a lot of times we're going to end up using piecewise functions in order to do that, okay? So let me show you an example of these techniques. On this problem right here, the first thing we'd try is direct substitution, but we end up with a 0 in the denominator. We know that's not okay. So we're going to factor this. and see if it will simplify. If it will simplify, then we're in good shape. That factors to x plus 1 and x plus 2. I can cancel this off. Now when we say cancel, we're meaning it cancels off to be a 1. So finding this limit is the exact same as finding this limit. So the answer is 1. Now, if we were to look at this graphically, and this is the nice part about knowing how these limit laws work and being able to do all of this algebra type stuff here that we're talking about, okay, you would have to graph this or throw it into a calculator and pick a bunch of numbers that are getting really close to -1 from both sides in order to come up with either graphic evidence or a numeric evidence for what the limit is, but you still wouldn't know for a fact what it is without doing something like this. Or at least considering, can anybody tell me what this graph looks like?
Would that be aligned with the whole at -1?
Very good. Okay, what happens right here when you cancel off that factor, when you cancel that to be a 1, okay, that leaves a hole in the graph. So it looks exactly like that linear function right there, crosses at 2, but it's got a hole at -1. So it looks like this. And guess where that hole is? At -1, 1. And the value of that y value at that hole is the limit. We're approaching it from this side and this side. Does it matter that it's got a hole there? Nope, because we don't care what happens at -1. We care what happens around -1, and it's getting closer to 1 from either side. Good there? Yeah.
When you plug in like a little higher than -1,
Mm-hmm.
it makes it answer +1. But if you get a little lower than -1, it makes it negative.
You can plug in like a negative. So think about it this way. A little bit bigger would be plugging in -0.99, okay? A little bit smaller than that, approaching it from the left side, would be plugging in a -1.01 or something like that. If you plug this in here, you're going to get something that's pretty close to +1. Is that okay?
I mean, like the denominator, when you cross it out, isn't it, you're going to cross out a -1 at the bottom? Obviously.
Nope, you're gonna cross off something that's really close to 0. Okay? When we cross these off, they're canceling to be a 1, a +1. Okay? Good, but don't overthink it. Okay. Got it? Okay, so there's an example of factor and simplify. Take a guess at what we're going to do here. We are going to rationalize the numerator. Take a look at why we have to rationalize the numerator. If I plug in a 0, I immediately end up with a 0 on the bottom. We know that's not okay. Take a look at what we get when we plug that into the top. Square root of 100 is 10 minus 10. I get a 0 over 0. Okay? I got some issues with this. Okay? So let's rationalize. So here's how we're going to rationalize. It works the same as rationalizing the denominator. We multiply by the, what's that C word? Conjugate. And a conjugate is just a fancy word that represents a difference of squares. So this is going to be the square root of x squared plus 100 plus 10. Square root x squared plus 100 plus 10. And then here's what we end up with. Limit as x approaches 0. Okay, watch carefully, please. Okay, when you multiply these together, whenever you multiply conjugates together, it produces a difference of squares. So it's going to be a square of this first term. Well, what do you get when you square a square root? You get x squared plus 100. You get whatever's underneath there. You get the radicand. Okay? Minus that squared. 100. Okay, now, the key to doing these correctly and not making too much work for yourself is please don't bother multiplying these together. Don't distribute the x squared through to each one of those terms. Leave it out here. So this is x squared and then just that conjugate that I multiplied by. So, and we're going to make sure we're clear on this. Those cancel to be a 0, completely gone. So now I only have one term on the top, and the only term on the top is an x squared. So I can cancel that factor on the top with that factor on the bottom. So now what I've got is this. I've got the limit as x approaches 0. What's left on the top? A 1. And here's the really cool part. What we've done is we've changed an expression that we could not do by direct substitution, just using some algebra, into something we can. What's the top? A 1. Now take a look at the bottom. That expression with a minus sign produces a 0. But that expression with a plus sign now produces a 10 plus a 10. So we get a 20. So the answer on that one is 1/20. Now, can you imagine throwing that into your calculator and plugging in numbers that are really close to 0 on either side, or graphing it and zooming in so you're really close and taking a guess at 1/20? 1/20 is 0.05, but a lot of the ones that we did on the calculator, or the ones that we did as guesses earlier this week, it was pretty clear it was getting to a whole number. Okay, doing things numerically or graphically where the limit is a fraction or a decimal is really hard. Okay, and here we're sure of what it is because we use those laws to figure it out, and we use direct substitution. Good there? Any questions? Okay, let's take a look at the next one. Any ideas there? Use a familiar limit. So I'm just going right in order here, but even if you're told use a familiar limit, yeah, we're going to use sine x over x. How are we going to get sine x over x out of that expression? Yeah. Okay, so from trig, one of those basic identities. Okay, tangent is sine x over x. So we're going to write this as sine of x. Whoops, so tangent of x is sine x over cosine x, right?
Yeah.
This is a complex fraction, so I'm going to think of it as a fraction on top, fraction on the bottom. I'm going to cross that one out, and I'm going to multiply. So this is the same as just using some basic algebra and a trigonometric identity. This is the sine of x over the cosine of x times x. And I'm going to put that in parentheses. Okay, and this is why you should practice at least a little bit of justification. We should maybe write one more step before we get the answer. I'm going to write the limit as x approaches 0, and here's what I'm going to do. Okay, please get used to this. I'll say this a couple times. Please lock this away. There are lots of times in pre-calculus where pretty much every single time we're taking a complicated expression and we're making it look very simple. So we're really conditioned to simplify things. In calculus, just like this example right here, rationalizing the numerator looks like we're making a mess. Making things more complicated or breaking them apart is actually a good thing many times in calculus. So let's take a look at this. We don't do this in pre-calculus very much, but I'm going to do this. I'm going to write this as 1 over cosine of x times the sine of x over x. Now, is that okay? You bet it is. Because really there's a 1 out in front there if I wanted to use it. So I'm doing 1 over the cosine of x, sine of x over x. I'm using the properties that multiply fractions together, the fact that we just multiply the numerators together and multiply the denominators together, to break this into a multiplication problem. This we know is its limit is 1, and notice how I've got the arrow, so it's approaching 1. I can't evaluate that by substitution, but I do know what the limit is. Can I evaluate this one by substitution? Yeah, I can. What's the cosine of 0? 1. So 1 over 1 is 1. So my limit is 1. Okay? Questions? Sure? Okay. All right, let's take a look at a couple of these here. Ideas on D. Well, the first thing what's that?
I was going to say, do the conjugate.
We could try that. The first thing we'd try is always try direct substitution. If you can plug it in, great. Try that first. Clearly, we've got an issue there because we're finding the limit as x approaches 0. Okay?
Can you multiply out the h plus 3 squared and then the 9 will cancel out and then factor out any h?
Very good. So the key here is to do this. We could multiply by the conjugate, but that's going to produce this stuff raised to the 4th and an 81. Okay, that's going to get a little bit worse. Okay, so what we're going to do here is we're going to actually square this out. Now the key is to make sure you square this out right. It is not 9 plus h squared. Please don't write that. Okay, those are the pre-calculus mistakes that will totally screw you over in calculus. Okay, this is 9 plus 6h plus h squared minus 9 all over h. I get to cancel the 9's. Like Maddie said, I'm going to take out an h. I'm left with 6 plus h over h. And then again, the whole issue with direct substitution was there was an h in the denominator. I can now cancel that, and I'm finding the limit as h approaches 0 of 6 plus h. So that's going to be 6. And it's that simple. Okay. Any questions? Okay. How about that one? What's that?
Use the number 4.
So consider one side. So let's find this. Let's find the limit as x approaches 0 from the negative side of absolute value of x over x. And let's find the limit as x approaches 0 from the positive side of absolute value of x over x. And let's maybe do the easy one first. Let's do this one. Why is this one the easier one to do?
Because they're both positive.
Okay. What type of numbers are we plugging in if we're approaching 0 from the positive side? Positive numbers. If you take the absolute value of a positive, it's still positive. It's just x, right? Okay. So this is the same as x over x, which is 1. In fact, if x is positive, it's always 1. Pick any positive number you want. Ugly positive number, nice positive number. Pick the square root of 13.2. I'd have the square root of 13.2 in absolute value on the top and the square root of 13.2 on the bottom. Still a 1. So everywhere over here, it's a 1. Does it exist at 0? It doesn't. So I'm going to put an open circle right there. Okay. What type of numbers are we plugging in here? Okay, we're plugging in negative numbers. So let's think about this for just a second. If I plugged in a negative 5, what is the absolute value of negative 5? It's positive 5. So if I plug in an x that's negative, how do I make it positive? I take the opposite of it. Let's do a number. Plug in negative 5. I get a 5 on top. What's on the bottom? A negative 5. Positive 5 over negative 5 is negative 1. Okay, and that will work with any negative number you plug in. Let's take a look at this. If I plugged in a negative 5, I'd have a negative 5 on the top, which would be positive 5, and on the bottom I'd have negative 5. Doesn't that still give me my negative 1? And if I cancel the two of these, doesn't that give me negative 1? Isn't that pretty good evidence that no matter what I plug in on the negative side, what value do I always get out? I always get out negative 1. And again, we'd have an open endpoint there. So I find the limit from the left is negative 1. I find the limit from the right is positive 1. Yeah, since I've checked the two sides and they don't agree, we'd say this one does not exist. It has both sides. It has a left limit and a right limit, but because they don't agree, it doesn't have a two-sided limit. Any questions? Okay, so we've got a couple more problems to look at. This is called the Squeeze Theorem, or some books call it the Sandwich Theorem. This book calls it the Squeeze Theorem. We're going to do a pretty simple example, and what I need you to do is I just need you to think about why this would be true, okay? It's called the Squeeze Theorem for a reason, okay? So it says we've got three functions right here. And it says we've got f and g and h. F is smaller than g and g is smaller than h. So which one's the smallest one? Okay, so this is the smallest. Which one's the biggest? That one's the biggest. And g is in the middle. And if we graphed these, we could say h is up here, g would be right here, and f would be right here. Now, it leaves open the possibility that they could actually equal each other, okay? So h could be up here and maybe swing down and touch it at some particular point, or maybe all the way along there. And f could be here and maybe touch it along there somewhere, okay? So small, medium, and large, top, middle, and bottom, however you want to think of it. Does everybody understand what the setup is here? Okay? We know the limit of f and h at the point of interest A is L. So we know the limit for both of these is the exact same number. And what we're able to conclude is, look, I know the limit of the big one, and I know the limit of the small one. I know they're both the same. Then the limit of the one in between them, right in the middle, has to be that same number L. So let's take our little picture right here. This made perfect sense a second ago, right? Okay, let's say this is our point of interest. And let's say this function value is L. So if this h is always on the top, and this f is always on the bottom, and we're not sure about g other than we know it's in the middle. If this one comes up here and squeezes down or pinches down or sandwiches down to the same point that h does, and the same thing happens to the right. This one kind of squeezes down here, and this one squeezes up here, and g's always in the middle. Can g wiggle around enough to get out of having the same limit right here? It can't. If it's always in between there, it's got to have the same limit. So we've got this function that we're not sure of, but we know what happens on the top and bottom, and we squeeze it in between those two to the point where, hey, we know what happens to this function right here. Does that make sense? Okay, let's run through an example. Okay, so what is the limit as x approaches 0 of cosine x?
1.
It's 1. What is the limit as x approaches 0 of 1? It's 1, constant function, all right? So I'm going to come over here, and I have a constant of 1, okay? So that is, I'm going to call that h of x equals 1. Then in red, I'm going to put the cosine function. Now, the cosine function, you'll remember, looks something like that, okay? So I'm going to call that f of x is cosine of x. Okay, everybody agree they have the same limit right at that particular point there? Okay, I'm really interested in at 0, okay? Now, the next statement is cosine of x less than or equal to sine of x over x less than or equal to 1, okay? Is that statement true? So I'm going to come over here, and we're actually going to sketch this on a graph. So you can just watch, okay? So I'm going to put in cosine of x. Then I'm going to put in sine of x divided by x. And then I'm going to do this one, 1. And I'm going to hit zoom. Okay, so there's cosine. There's that sine of x over x. And there's 1. Okay, and let's do this. Let's zoom in. Let's zoom in right here. There's cosine. There's sine of x over x. Okay, does it look like that's true? Does it look like sine of x over x is in between cosine on the bottom and 1 on the top? Okay, I'll let it go one more time, and we'll look at it a little more closely, then I'll show you what the window is. I want you to just, I mean, this is pretty good evidence. This isn't a proof, but we're going to get pretty close. We'll actually prove this, I think, later on in this chapter. Okay, so pretty good evidence? Okay, so I'm going to come over here and I'm going to graph what sine of x over x looks like. Okay, looks something like this and like that. And it says, use parts A and C above and the squeeze theorem to find that limit. Well, we already know what the limit is, but here's what we're going to do. I take that expression right here, I know this limit. I know that behavior really well. I know this one right here. This is what I'm not sure of. So here's what we do. We take a limit of each one of these. So the limit as x approaches 0, cosine of x, less than or equal to limit x approaches 0, sine of x over x, less than or equal to limit as x approaches 0 of 1. Now remember, we said we know the behavior of this one really well and we know the behavior of this one really well. Well, what is this limit? This one right here. It's 1. What is this limit right here? Okay, now before I fill in the middle part, if you've got a number that's greater than or equal to 1 and less than or equal to 1, what's the only number that could possibly satisfy that? A 1. So this has to be a 1. So whatever this is, it's got to be a 1. So that right there, change colors here. This right here has to be 1. Okay? All we did is we just squeezed that down to the point where it didn't have any wiggle room. It's got to be a 1. Okay? Any questions? And again, we can't use the law for quotients or any of those laws that we learned today because the denominator is a 0. We've got that domain issue. Okay? Any questions? Okay. I'm just going to leave you with an interesting challenge problem. If you've got this function right here, where is that function defined? What's its domain? So 0 to infinity. You can plug anything you want that's as long as it's a positive number into a logarithm. Okay. Can't take the log of 0 or a negative, so we got to throw those out. We're right here right now. Anybody concerned about anything else? What else can we not let that? We've dealt with a logarithm, but we've got a division problem right here. What can we not divide by? Can't divide by 0. Is ln of x ever equal to 0? Yes, it is. When? When x equals 1. You could exponentiate both sides and see what that would be when x equals 1. So there's another number that we can't use. We can't use a positive 1. So if we were to think of what the graph looks like, it doesn't exist over here. It exists over here everywhere except for there's something going on right here, something weird going on at x equals 1. Maybe a vertical asymptote, maybe a hole. Is it a hole? No, because it doesn't cancel. It doesn't cancel. So there's going to be a vertical asymptote right here. So where would be the most interesting point or points to find the limit on that particular function? At x equals 1 and maybe 0. So maybe you'd want to find the limit as x approaches 0 from what side? The positive side. Oops, x minus 1. Maybe you'd want to find the limit as x approaches 1 from the negative side. And the limit as x approaches 1 from the positive side, x minus 1 over ln x. Now, I think that you could figure out each one of those three using the ideas that we talked about yesterday. Remember that whole idea of, I'll help you out here. If I plug in a number that's really close to 1 from the positive side, in other words, a really small positive number, what's that turning into? First of all, is it positive or negative? Negative. Plug in a number, plug in 0 if you want. it's negative and getting really close to a 1. Remember how you separate those? What happens when you plug in a really small positive number into ln? You get a positive or negative number? Oh, disappointing.
Oh, it does.
That's what ln looks like. If you plug in a really small number, you get a negative number that's really huge. Okay, that's enough of a hint. Think about those for a while. I think you can figure out what the answer is, and if you can, it's going to lead us into what we're covering in, I think, 2.5. Okay, you don't have to do this, but if you can figure this out and figure out whether, does this increase without bound, decrease without bound, throw it in a calculator. It'll graph. Hopefully you get the graph right. Okay. All right. Let's see. So for 2.1.